Hello, welcome back to lecture. Today we're going to be talking about random variables. This is section 5.1. So let's think about this. If we roll a fair die, put this down here, the possible outcomes are the numbers 1, 2, 3, 4, 5, and 6. And each of these numbers has probability 1/6. Rolling a die is a probability experiment whose outcomes are numbers. The outcome of such an experiment is called a random variable. So we do an experiment, we'll get that random variable that could be the 1, 2, 3, 4, 5, or 6. So a random variable is a numerical outcome of a probability experiment. Discrete random variables are random variables whose possible values can be listed. So the outcomes are finite, we can list them, and then they have an association, some probability with them. There are two types, discrete and continuous random variables. Discrete are numbers that you can count 1, 2, 3, 4, 5, 6, 1, 1.52, 2.5. So they become in discrete values. A continuous random variable, or just like it says, they can be anything continuous. So weight, if you consider something as a weight, it could be anything, you know, the 1 pound, 1.1 pound, 1.0001 pound. So there's a lot of numbers between the two. Anytime I find two numbers, I can go halfway between them. So the number that comes up on a roll of a die would be a discrete random variable. The number of siblings a randomly chosen person has is a discrete random variable. We grab a person, how many siblings do you have? So continuous random variables are random variables that can take on any value in an interval. So the examples include the height of a randomly chosen college student, the amount of electricity used to light a randomly chosen classroom. So we've talked about probability distributions before. The probability distribution basically for a discrete random variable specifies the probability for each possible value of the random variable. So properties, we've talked about this. Probabilities go from 0 to 1, 0 less than or equal to the probability of that x showing up, less than or equal 1 for every possible value x. And the sum of these probabilities equal 1. That makes a probability distribution. So here's one, and we want to decide if this is a good probability distribution. My outputs are the numbers 1, 2, 3, 4, so that's okay. Probabilities, 0.25, 0.65. Now here I've got a negative probability. All probabilities have to be between 0 and 1. So this would not be a good probability distribution. So what about this one? Here I've got x being a -1 and -0.5. But that's okay. It's just the probabilities that need to be between 0 and 1. And if I add these up, I need to add them up and be equal to 5. And this looks like, I believe, is going to be a good probability distribution. Okay. So all of the probabilities are between 0 and 1, and they add up. If I add up all these probabilities, they add up to 1. Here's another one. The x's are okay. These can be 1, 10, 100, 1,000, just a finite listing of numbers. But here I've got a probability that's already 1.02. They have to be between 0 and 1. Now, if this was guaranteed probability 1.0, that would be fine. And as long as all the rest of them were 0, they would sum to 1 and we would be okay. So 4 patients have made appointments to have their blood pressure checked at a clinic. Let x be the number of them that have high blood pressure. So the probability distribution of x is as follows. 0, 1, 2, and 3, 4. 0 is none of them. 1, 2, 3 are all 4. And it's asking me to find the probability of 2 or 3. So this we learned before when we're doing the when we're doing an OR function. It could be this probability or this one, and we just add up these two. So it would be the 0.27 plus the 0.8. 0.08. That would be probability of 0.35 that either 2 or 3 of them would have high blood pressure. So again, let's look at another version. Find the probability that more than one, so more than one would not include 0. It has to be more than one, so only 2, 3, or 4. So we would add up the 0.27, so it could be 2, x equal 3, or x equal to 4, and we would just add up the 0.27.08 we saw as 0.35, and here would be 0.36. What about the probability at least 1? So at least 1 is at the very smallest, at the very least. I like to consider this as the very least 1, but it can be bigger. So at least 1 would be the 1, or the 2, or 3, or 4 would satisfy this. We could add up all of these things, 0.41 plus 0.27 plus 0.08, 0.01. But when I'm doing this one, I'm seeing the only one that we're not including is the 0. So if I had a lot of these, instead of adding these up, I'd say, well, I know if I've got a good probability distribution, I sum these up, they're equal to 1. If I just subtract off this one, then that's got to be the rest of it. That's the complements. So I'm either this or the rest. I'm not this or not this, and that's kind of the not this is the 1, 2, 3, or 4. So here I'm just going to say that's the probability of 1 of everything minus the 0.23 that I know. And that would give me 0.77. Frequently we'll find that that's easier to calculate if we've got a large table, that I can just say for at least 1, that's that. If I've got less than 4, I can do the very same thing. That would be 1 minus 0.01 would give me the 0, 1, 2, 3. So here's just a general statement, kind of read over this thing. Basically, we do a lot of drawing samples from populations. If we've got a good idea of the probability distribution based on populations, if we go and grab a sample out of that population, we can use those distributions to kind of understand things about samples of what we're looking at, how values could turn up, so we can say something about the probabilities. Okay. So an airport parking facility contains 1,000 parking spaces. Of these, 142 are covered long-term spaces that cost $2 per hour. 378 are covered short-term spaces that cost $4.50 per hour. 423 are uncovered long-term spaces that cost $1.50 per hour, and 57 are uncovered short-term spaces that cost $4 per hour. A parking space is selected at random, so I go into the parking lot, I just kind of drive around for a few minutes, and then I just say, oh, there's one, I'm going to pull into that at some time later. So I'm going to set this up as a probability distribution. Let X represent the hourly parking fee for the randomly sampled space. Okay, so here I've got the versions are the 152, 450. So I know my X's. So I'm just saying I pull into this randomly selected space. What is the probability that I'll pay certain values of these things? Okay. So here's the possible values of X, 152, 450. And what about the probabilities of getting into that? Well, this is just basically a theoretical probability problem. I have 1,000 parking spaces, and I know how many each one of these are. So the probability I would get into there would be the 142 over the 1,000. So let's see how that works. So the probability of 150, the number of spaces costing 150, there was 423 of those out of the 1,000. So the probability would be 0.423. Let me pull myself back up here. The probability that I got a $2 space, well, there's 142 out of 1,000. Probability 0.142. The probability of a $4 space is 57 out of 1,000. That would be probability 0.057. And then the 450 would be 378 out of the 1,000, and a probability of 0.378. So if I add up all of these, I should come up with 1,000. 1,000 over the 1,000, that's the 1. So that should be everything that we need. Okay. So here's a probability histogram. So we need to basically draw that bar graph that looks, and that's our probability histogram. So here's another example. The following represents the probability distribution histogram for the number of boys in a family of 5 children. Using the assumption that boys and girls are equally likely and that births are independent events, you just basically come up with this probability, and we'll look at it a little bit later to see how we can develop something like this. But we list the x's, here's the probabilities, and we know we've done this many times before of just building that histogram, and this is what that would look like. Here's the probabilities from here, the relative frequencies basically, 0, 1, 2, 3, 4, and 5. And we can see that's a very symmetric bell-shaped curve. So we could use things like the empirical rule for this. So we've got a random variable. We've got the probability, so we've got that distribution. So what would be the expected number that would come up? What would be the most likely that this thing would be? Okay. So the mean is a measure of center, and the mean of a random variable provides a measure of center for the probability distribution of a random variable. To find the mean of a discrete random variable, multiply each possible value by its probability, then add the products. So we're just going to add up each x times its probability, add those up, and that's going to turn out to be the mean. Okay. So let's see how we're going to do this. So a computer monitor is composed of a very large number of points of light called pixels. It is not uncommon for a few of these pixels to be defective. So let x represent the number of defective pixels on a randomly chosen monitor, and the probability of distribution of x is as follows. Find the mean number of defective pixels. So if I went through and did 1,000 displays, what would be the average number of pixels that were defective? And that's what this is saying, so the mean number of defective. So if I grabbed 1, the probability that none were defective is 0.2. Only 1 out of the 3 was defective, 0.5. 2 out of the 3, 0.3, and 3 would be 0.1, I'm sorry. So 1 pixel would be defective, 2 pixels, or 3 pixels defective. So what we're going to do is multiply each x times its probability, and then just add these up. So the mean value of these, the mean number, the expected number of pixels of being defective would be 0 times 0.2 plus 1 times 0.5 plus 2 times 0.2 plus 3 times 0.1. So I would expect if I went out and did 1,000, the average number of pixels that were defective would be like 1.2. So let's say if we imagine each rectangle in a probability histogram to be a weight, the mean is the point at which the histogram would balance. So right in there. Okay. There are many occasions on which people want to predict how much they are likely to gain or lose if they make a certain decision or take a certain action. So often this is done by computing the mean of a random variable. In such situations, the mean is sometimes called the expected value. The expected value is just the mean, and it is denoted by the expected value of x. So if the expected value is positive, it is an expected gain, and if it is negative, it is an expected loss. So I do some of this thing where maybe I've got some money in there. Sometimes I'm going to lose, sometimes I'm going to win. And the expected value is how much money I'm going to do, but it's the same thing as that mean. Okay. So a mineral economist estimated that a particular venture had probability 0.4 of a $30 million loss, probability 0.5 of a $20 million profit, and probability 0.1 of a $40 million profit. Let x represent the profit, and then find the probability distribution of the profit and the expected value. So does this venture represent an expected gain or expected loss? So you can kind of consider this as, let's say we're going through and doing drilling for oils, okay? We sink a bunch of wells, and it's going to take usually maybe some investment of $30 million to put a well up. 40% of the time, I do not get any use out of this. So I don't strike oil. It's basically a loss. 50% of the time, I strike oil and I make a big profit, a $20 million profit. And then sometimes I actually hit a very good well, and that 10% of the time, I actually make $40 million profit. So these were twice as productive. So if I keep doing these a large number of times, what is my expected gain out of these? So if I did one, I might lose the 30 million, but if I keep doing these all over, what am I expected to make? So here is my probability distribution. The negative 30, that's my $30 million loss. Probability 0.4, my $20 million gain at probability 0.5. A $40 million gain at probability 0.1. My expected value, so during my investments, my return on investments is basically the sum of these, the negative 30 times 0.4, 20 times 0.5, the x times p of x in each case, and that gives me a 2, or an expected return on my investments of $2 million. If I do enough mineral mines or wells, this is what I would expect to make. So we've also seen how not only the mean are we interested in, we're also interested in the standard deviation. So the variance, that's basically our starting point for getting our standard deviation. The way that we kind of look at this is that we go through it first, we find our mean or our expected value, and from each of these, from the x, I subtract the x, the mean value from the x, I square it, and then I multiply it times its probability. I add all of these up, and that's my variance, my standard deviation squared, the variance, and then I can take the square root of that. So here, if I'm just doing these by hand, instead of doing all of these subtractions and then square and then times its probability, it turns out it's easier. I've already got to get this mean, the x times the p of x. If I set this up in Excel, all I need to do is just square the x and then multiply its probability, add these up, and then subtract the mean from these things. So the mean squared, and that's an equivalent calculation. I do all the sum, and then once I just subtract off one, the mean of these things. In each case, either one of these are going to give me the same thing, and my standard deviation is just from taking the square root of the variance. Okay. So if I'm doing a TI-84, I can also do this on my 36. I can do these, enter my values of the random variables into L1, the probabilities in L2. We've looked at this before. Do the stat, calculate one var stats, and then it asks me which one you want to do them on. I want to do L1 and L2 as the arguments, and it'll run these things through. So if I were doing this with the TI-84 plus, here's my L1, enter these in the L2. There's L1, L2, my one var stats, L1, L2 command. And then this would give me, here's the mean, that's the mu of x. And then this is either my standard deviation or of the standard deviation of the sample or standard deviation in terms of the population. So assuming that this is a population, that would be what we would use. The variance, if I've got the standard deviation, I always have the variances. I'll just square these numbers here, okay? And that's why the S of X is not filled in. That assumes that we're talking about a population if I've got these as the distributions. So far we've covered the difference between discrete and continuous random variables. We'll do more with continuous random variables as we go forth in the course. How to determine the probability distribution for a discrete random variable, the outputs along with their probabilities, how to construct a probability distribution. So we can look at a graph and look at that distribution, the histogram, how to compute the mean, the variance, and the standard deviation. So I hope you found this informative. We'll see you next time, and have a good day.